Hello, welcome to the second of a three-part series on nutrient removal testing at wastewater treatment plants. In this session, we'll be covering phosphorus. My name is Nicholas Willis. I'm a senior program manager at the Environmental Finance Center at Wichita State University. So a brief agenda of this session is threefold. First, we're going to answer the question of why are we testing for phosphorus? Then we're going to look at where to test for phosphorus within our plants, and then how to test for phosphorus. So why are we testing for phosphorus? For many people who've been in the wastewater industry for their entire careers, this might be a newer item for you. Phosphorus is being increasingly regulated with new limits and monitoring requirements in many permits throughout the United States. Other plants are facing decreasing limits, and these would typically be plants that have been in place for some time, where the water quality has not improved enough and additional phosphorus reduction is called for. We're also looking at phosphorus in wastewater treatment plants because other options have not gotten us where we need to be yet. So for example, I remember when I was a young kid, you would occasionally see news stories about detergents. Detergents used to contain, household detergents used to contain significant quantities of phosphorus. They no longer do. So kind of that low-hanging fruit's already been plucked, and the removal has to take place elsewhere, and oftentimes that's ending up at municipal wastewater treatment facilities. Another reason to test for phosphorus at your plant as a process control item is that many plants are utilizing chemical for phosphorus removal. If you can set up a testing regime and save on chemical cost, it can be well worth it. Oftentimes chemical expenses are 5 or 6 or even 7-figure items in the budget. So it is well worth it in many cases to try and optimize chemical application and chemical dosing for phosphorus removal. The important thing here is that you can remove phosphorus kind of two ways or in combination. So it can typically be removed biologically and or chemically. Another reason to test for phosphorus is that biological phosphorus removal requires proper environmental conditions. Phosphorus testing when the plant is working helps troubleshoot when it's not functioning well. So understanding what your biology is doing when the biological phosphorus removal is clicking along will help you to troubleshoot where something might not be working right, what process in the plant is not functioning well when the biological phosphorus removal drops off. Hopefully that won't be happening, but it is additional information to help you as an operator. So where are you going to test for phosphorus? Broadly speaking, most plants you're going to test in an anaerobic or a fermenter zone if it exists. Many plants do not have that. You will also be testing at the overflow of your aerobic basins, and then both before and after chemical addition, if you have it, and then at each potential location downstream where solids may settle. So for many plants, this would be the overflow of your clarifiers. So there might be some sort of a basin or a box there. There might be a splitter box where solids could potentially settle out. There also may be areas before tertiary filters or UV lights, or even if you still have chlorine disinfection, that would be another potential location. The idea here is that unlike nitrogen, which you ultimately remove to the atmosphere, phosphorus can only exit your plant either dissolved in the water, which is what we're trying to prevent, or attached to a solid, so as part of the biosolids process removals. And if you have an area downstream of your treatment where solids may be settling, that is a potential area where they could go anaerobic and release some of that phosphorus you've worked so hard to remove earlier on in your treatment facility. And then if it re-releases the phosphorus there, there's no place to remove it downstream. So it exits the plant in dissolved form. So kind of what we're looking at is understanding a phosphorus profile in your plant. So when your plant is working well from a biological nutrient removal perspective, test for phosphorus at the available locations, and your plant may not have all of these. So you would look at the influent coming in, the anaerobic basin, so the outflow of the anaerobic basin, the outflow of the anoxic basin, the overflow of the aeration basin, past any clarifiers you may have, and then at each downstream process further. Again, we're looking at locations where potential settling of solids, any suspended solids that are getting past your clarifiers could occur and release phosphorus back into the water column. So when we're looking at this, the phosphorus values, approximately, each plant is going to be different. Your anaerobic basin and your anoxic basin, the phosphorus values would often be about 2 to 3 times the influent. And this is part of the fermentation cycle. So the first step in phosphorus removal is to add more phosphorus to the system. It's pretty counterintuitive, but it does work. Then that phosphorus is consumed in the aeration basin. And the overflow of the aeration basin, and this will be, again, supernatant from the settled mixed liquor, is going to be the lowest value in the plant in most cases. So this is after the biological nutrient removal has been complete, and then it's just a matter of separating the solids out from the liquids. So your lowest value in the plant should be at the overflow of the aeration basin. Then if you're looking at the water coming out of your clarifiers and each downstream process, such as UV or tertiary filters, you want that to be within about 0.1 milligrams per liter of the lowest value in your plant. So that would be the overflow of the aeration basin in most cases. So basically, you do this enough times and you understand when your system is really dialed in, when it's working well, what the relative value should be. And then if you do a profile when things aren't working well and you find out, well, I sampled at my UV and the phosphorus level was much higher than 0.1 milligram per liter above what's coming out of my clarifiers or what's coming out of my aeration basin. That is an indicator that you likely have an issue with a UV channel, perhaps our solids settling there, and you can explore further. So it's very much a troubleshooting operation. So there may be some special cases here. I've worked with plants that have batch discharges. The beauty of a facility which has a batch discharge and a phosphorus limit is that it's pretty easy to ensure compliance because you just add more chemical before the discharge occurs. So you can typically get that compliance with chemical. However, testing for chemical rather than just adding what you added the last time could save a lot of money. So you test for phosphorus, find it's within your permit. You don't have to add any chemical to be in compliance. You might also test your influent if excessive loadings or spikes are being seen elsewhere in your system. Industrial samplers are also a good idea to sample, especially if you have an industry that is discharging high levels of phosphorus or that you suspect they might be. Those sampling points in your collection systems can really pay off there. Additionally, and I really want to stress this one, is dewatering and decanting flows. So many times plants can have significant internal loading of phosphorus from their biosolids operations. I've personally seen levels of about 40% of total phosphorus entering aeration basins is coming from biosolids operations. So you're recycling that phosphorus, and you just have to work harder to remove it that way. It's a less than ideal situation, but understanding what those loadings are is important. So it's important to understand those dewatering and decanting flows, because if you're not dewatering, if you're not decanting on a regular basis, you might kind of be shock loading the system. So it is best to decant and dewater regularly, especially if you're relying on biological phosphorus removal. If you are relying on biological phosphorus removal and you increase phosphorus loading by 30 or 40% because you begin biosolids processing. That's a good way to really kind of exceed the biological capacity of the organisms within your plant to absorb that phosphorus. So that's an often can be a hiccup point, that dewatering and decanting flows, when it comes to having reliable biological phosphorus removal occur. So how do we test for phosphorus? First, I really want to stress it's important to ensure you know what the test is reporting. So for most process control, you're going to be testing for orthophosphate. And that is the dissolved form of phosphorus that's generally present in wastewater treatment facilities. These are pretty quick tests. Typically reaction time is 7 to 15 minutes. And there's no digestion, which occurs, no heating in an oven, which is required. For most testing purposes for process control, you want to use that orthophosphate just because it's quicker, it's cheaper, and assuming you have good suspended solids removal, the majority of orthophosphate leaving most wastewater treatment, the majority of phosphorus leaving most treatment plants is or in the form of orthophosphate. So that's really what you're targeting for removal. Now you want to use total phosphorus for compliance. That's what it is in most permits. For most facilities, this is being done at an outside lab. Digestion is required, though I have worked with facilities that are doing that in-house. It becomes more important to test for total phosphorus as you get more stringent limits, because you have just less leeway when it comes to not knowing the entirety of your result. Because using orthophosphate, your reading is almost always going to be a little bit low compared to the total phosphorus in your plant. And that's okay for process control for most facilities, but if you do have very stringent limits, being able to do that total phosphorus in-house may be something to consider. Color wheels are available for testing phosphorus. These are pretty good for process control. You do need to be careful a little bit when it comes to the accuracy of them, and try to get a color wheel that has more points, that is more sensitive within the range you need it to be. So you may need it to be under 2 milligrams per liter might be your permit limit. So you don't want a color wheel that goes up to 10 or 15 milligrams per liter. You want one more in that 2 to 4 milligrams per liter. So ensure that you're getting the right thing. Ideally, a digital colorimeter or spectrophotometer is more desired. These are just more accurate. They avoid color blindness issues. These are likely necessary for more stringent limits. And for many facilities, phosphorus limits end up being more strict than ammonia limits. So you're more likely to have a phosphorus limit below 1 than an ammonia limit below 1, at least on a year-round basis. Many of the colorimeters and spectrophotometers have the ability to connect to computers, and that really helps with the logging and tracking of data. It is also easier to dilute as you are doing these tests in a laboratory. So you grab the sample outside and then bring it into the lab. Dilution is often required, particularly if you're doing some of those internal flows off of decant water or belt filter press flows, because often the phosphorus is very high there. So the ability to dilute is important, and it's important for you as operators, as laboratory techs, to understand what and how to dilute and know how to do the calculations to get the actual value. Another thing with the colorimeters and spectrophotometers is that almost all of them are going to have other parameters that you may need to be testing for. So that's much better than the color wheels, which are all kind of everything I've ever seen has been a single test product. We will now be moving into phosphorus sampling at various treatment plants, kind of in the real world. So if you were looking at the phosphorus profile in these plants, this is where you'd begin sampling. So Ellenwood, Kansas is a 2-cell sequencing batch reactor. It does have an equalization that takes the decant from the SBRs to smooth the flow going into the UV disinfection. If we were going to do either profile and or troubleshooting for phosphorus removal at this plant, we would take at the influent, we would also take the decant from each basin, because one basin may be removing phosphorus better than the other one, and that would be important to know. And with kind of SBR basin timing, you may want to take it at different times of the day as well, because the influent hitting the basin, in the middle of the morning is quite a bit different than the influent hitting the basin at midnight or 3 a.m. So there may be some differences coming off the decant depending on the time of day. You also want to look at that EQ basin influent. So that is going to be the mixture of the two SBRs, and then the EQ basin effluent. The EQ basin is something we want to look at because it's a big tank. And if there's any suspended solids leaving the SBRs, they're likely to settle out in the EQ basin. And settled solids are kind of the enemy of reliable phosphorus removal because they can go septic and re-release that phosphorus. So the EQ basin is a high suspect if you're going to have kind of solids settling out there. Finally, we'd be looking at the UV effluent, making sure you're not triggering reporting requirements in that sampling. But the UV infrastructure typically has a place where water's slowing down as it goes into the area where the lights actually are. There may be a sag in it where solids can settle. So that's kind of what we're looking for at an SBR plant. Your plant will obviously be a little different. If you're looking at this for your own facility, feel free to reach out to me and we can go through it to help you build a good first start for how to profile your own plant. Now, we're going to move on to kind of the basic oxidation ditch here. This is in Buhler, Kansas. Everything's labeled. For profile and troubleshooting, this is a little simpler than the SBRs because it's a simpler plant. We're going to be looking at influent here, and then the oxidation ditch overflow. So that's before the final clarifiers. You're also going to be looking after the final clarifiers and then after the UV light. So every location here past the aerobic treatment basin, so the oxidation ditch in this case, is a potential place where phosphorus, once it is bound into the solids of the plant, can get re-released. And that's really what we're looking for here. Your plant may have other structures between, say, the oxidation ditch and the final clarifiers, or the final clarifiers and UV disinfection. Often there's flow control structures, and that is going to be something you want to look at. Is there a potential for solids to settle here? And if so, that is a reasonable location to be sampling for phosphorus at your plant for that phosphorus profile and for troubleshooting purposes in the future. Now, many facilities are parallel plants. This one is a Schreiber system in Edgerton, Kansas. Before devising your profiling scheme, it is important to understand how parallel these plants are actually operating. Many plants like this will mix return activated sludge. So they're more of a sort of parallel plant and not fully parallel treatment facilities. It's also important to understand if the plant is set to really provide equivalent flows and loadings to both basins. Sometimes they are not, where one basin may take a higher percentage of flows than the other one. And that will help you figure out how you want to run your phosphorus profile. Another thing you might look at is sludge blanket depth. If you have more than one final clarifier, are they being run in similar manners or not? The more parallel basins are operated differently from one another, whether it's operator decisions doing that, or perhaps there's infrastructure issues causing better treatment to come from one basin than the other. That is going to be a kind of a red flag to take more samples, to err on the side of having too many samples rather than too few. So for profiling and troubleshooting this plant, we're going to look at the influent, just like every other plant, and then before each clarifier if possible. And the reason you want to do before each clarifier is that that is going to tell you whether or not the aeration basins, as the water leaves the aeration basins, whether the biology in the aeration basin has caused phosphorus to be consumed and put into the biology of the plant. You also want to look after each clarifier. So clarifiers remove the solids and provide clear water, but the sludge blanket can sometimes cause phosphorus release to occur if it goes septic. So that is why you need to understand how your clarifiers are operating, and if you're operating them in a similar manner or not. So you may have one clarifier that is causing problems and one that is not causing problems. And it's important to understand the dynamics of your clarifier operation there. Finally, for this plant, you'd be looking before the UV light, because there's kind of a conjunction box where the final clarifier waters come back together, and then after the UV light, as there's possibilities for solid settling to occur in most UV configurations. Moving on to a biological nutrient removal plant. This is from Wellington, Kansas. For profile and troubleshooting, you're going to have more samples than many other facilities. Again, we are very interested in our plant influent. We are also very interested in the exit of the anaerobic fermenters. Some plants, you're going to have to devise how you're going to sample because there's not necessarily a discrete point of flow. It's important to be consistent from sample point to sample point and from week to week, month to month, where you are grabbing your samples. You also want to look at the exit of the anoxic zone. We see that many biological nutrient removal plants, what is designed and how it is operated is not the same thing. So perhaps the anaerobic fermenters never get anaerobic, and the anaerobic growth occurs somewhere in the anoxic zones. Sometimes neither is happening, where you never get anaerobic or anoxic conditions occurring at plants that are designed for biological nutrient removal. So it's important to profile in each discrete basin here. Then you'll also want to be looking at the exit of the aeration treatment basin. So there's a weir to the clarifiers as labeled here. This plant has 2 final clarifiers. You'll want to sample the water coming off of each of those. And then you'll also want to be looking after the UV light. And then this plant has a pond system where effluent can be directed to. And that effluent control structure may be a potential location where solids have settled and are releasing orthophosphorus back to the water. So that's another point. You'll also want to, if you have a polishing pond or an effluent storage pond and you're discharging from that effluent storage pond or those polishing ponds, you'll want to sample the water in there as well. Because that is a potential location where phosphorus may be released. They are also locations where phosphorus can be added from animals, from runoff getting into the pond. There's kind of a plethora of ways that the effluent storage pond can interfere with phosphorus levels at your plant. So understanding what is going on there is also important. Now we're going to move to kind of a more straightforward activated sludge design. This plant is in Kansas City, Kansas, plant number 20. Again, your phosphorus testing, always need to know the influent. In this one, we're going to try and understand what is happening after each process step, similar to the other plants, but this one you have primary clarifiers first. So you take the sample of the influent, and then at the exit of each primary clarifiers, you should have some release of phosphorus or some decline of phosphorus from the primary clarifiers. You also look at the exits of the aeration basins. I believe this plant has 3 aeration basins, so there would be 3 sample points there. You'll also look at the exits of both final clarifiers. Look at the water immediately before the UV and after the UV at your facility if you have one like this. There's also other tests for phosphorus removal that can play a key role. So ammonia, we have a training on ammonia, but ammonia is a good proxy for the suitable amount of aeration needed in the aerobic zone of your plant. If you have low ammonia in the water coming out of your aeration basin, that indicates a very good likelihood that you have enough air to remove phosphorus if you have the organisms in place and food is plentiful. BOD and COD. Biological phosphorus removal requires significant biochemical oxygen demand for organisms to thrive. Low BOD influent may impair biological nutrient removal. So you can have everything right, but if there's no food for your biomass to consume as they're taking up that phosphorus, they won't take up the phosphorus. So having enough carbon in your system is important. And your BOD, or if you're using COD as a proxy, can help diagnose trouble with biological phosphorus removal. pH generally needs to be above about a 6.8 for biological phosphorus removal to occur in a plant. Nitrates, we have another training on this. Nitrates will interfere with the growth of phosphorus accumulating organisms. You really need to ensure that there's low nitrate levels in your fermenter areas. In my experience, plants with high nitrate levels in their discharge rarely have very good phosphorus values unless if they're adding chemicals. So if you have a nitrate issue in your plant, it's likely to cause interference with biological phosphorus removal efforts. So oftentimes your first step is to reduce nitrates, and then you go after phosphorus biologically. Sulfate and or chlorides. Metal salts, if you are adding chemical to reduce phosphorus, metal salts are typically paired with chlorides or sulfates. Your permit may have testing requirements. Your receiving water body may have total maximum daily loads for sulfates or chlorides. It's important you understand what is going on because it can impact your ability to remove phosphorus chemically. You may have to, change out your chemical for another one in case of chloride or sulfate impairments or limits at your plant. I'm going to bring up pH one more time here. If you are adding chemicals to your plant, oftentimes, and it depends on plant buffering and the addition of chemicals needed, pH is going to drop as you add chemicals. Typically your metal salts, so ferric chloride, ferric sulfate, aluminum sulfate, are all acidic. So they reduce the pH of your water, they consume alkalinity. Moving on to alkalinity. Alkalinity is typically going to drop with chemical addition. And this may inhibit ammonia removal, especially if your plant has high return rates. So if you have really high return activated sludge rates, you're returning lower alkalinity water back to the plant. Eventually that should reach kind of a new equilibrium, but that equilibrium may be too low of alkalinity and could cause issues with ammonia removal at your facility. So that's something to keep an eye out for as well. With this, we are wrapping up our training on testing for phosphorus removal at your plant. If you do have nutrient removal issues at your plant, feel free to reach out to me. I can provide technical assistance if you treat less than 1 million gallons per day. So you might be permitted for 1.5 million gallons per day, but if you're flowing less than 1 million gallons per day on average, your system is eligible. Best contact is by email. You can also dial my direct number as seen here. With that, we are wrapped up for phosphorus removal. Thank you.